Hey, Vlad here from ZIO.com. Welcome to another video. Today we're going to continue learning about ZIO, and we will also build in an error channel into our toy ZIO implementation. And sort of accidentally, we will spend the majority of this video learning about variance. Ooh, let's get right to it. All right, so this is exactly where we left off, and if we were to switch to the real ZIO, we would be able to fail because it has a factoring method for failure. As a reminder, we can just go over here and we can do ZIO.fail, and we can do boom with a string, or we can also do runtime exception, like this, boom, or we can also do throw runtime exception, even though it is technically incorrect. As a reminder, no library can fully protect you from things like exceptions or nulls. And the proper way would be to use another factory called effect, which simply has a try-catch block inside of it. In fact, we're going to have our own version by the end of this video. So let's build the error channel into our ZIO as well. Now, a long time ago, when this channel was very, very small, yes, even smaller than it is now, I made a video that compared the mathematical functions to programming procedures. My point was essentially that procedures in programming differ too much to be confused with functions in mathematics, even functions in the functional programming sense, because functions in functional programming are said to be referentially transparent, which means that they don't break the substitution model for procedure application, which means that you can take their value and inline it in all the places where you call this function. Now, mathematical functions are not just referentially transparent, they're also total. For instance, in programming, 3 divided by 5 cuts off some precision. Instead of returning something like an option of int that would be more type safe, right? It would be more total. However, for convenience and performance reasons, it's not done like this in the majority of the languages. The same thing for deconstructing a functional list. Even to this day, list.had throws an exception. Obviously, there is also a had option, but still, it exists. It's not a total function. Also, the classical example of Fibonacci, in its naive implementation, it is actually not that useful to you that it is referentially transparent if it never finishes. Now, if you wanted to make functions total, we would follow a pretty standard type progression. A function that always manages to retrieve a value of a is simply going to return a. A function that sometimes fails to retrieve a is going to return an option of a. A function that is going to fail to retrieve the a for different reasons is going to return either an error or the a. A function that can fail for different reasons at the same time is going to return either a non-empty list of errors or your value a. A function that might take longer to produce the result, like the Fibonacci example, is going to return some wrapper, like in tagless final it would be f. In our case, it's going to be ZIO of and either of an error or a. If we take a look at our implementation, in fact, let me close this one, and let me actually move this one to the left. If we take a look at our implementation, we're going to see that we already have an a, and we obviously already have a ZIO. So all we need is to build in an either in there. Let's actually go to main and remove this part and go back to using our own ZIO. And we're going to commit what we have so far. So I'm going to go back to my terminal, and I'm going to show you my alias called AGI, which simply is going to do git init and then throw everything that we have, right? So git init, just throw everything into the first commit. So we're going to go to our ZIO, and we're going to say that our ZIO might succeed with an A, or it might fail with an E. Now, usually if you're dealing with a lot of parametric types, you're going to start calling them, by the alphabet, right? You're going to go A, B, C. But in this case, arrow and E, kind of fits. So now our thunk is not going to simply produce an A. It is actually going to produce either an arrow or a. Now, I'm not going to save this file for a while because it's going to be read all the time. So the next thing that we're going to do is we're going to go and we're going to fix our factories, right? Which is the succeed over here, right? So we're going to fix the succeed and we're going to introduce in the fail, okay? Now, ZIO always has 2 parameters, and this particular one is never going to fail, and therefore we're going to use nothing over here. Nothing is a type that doesn't contain any values, and if you cannot produce a value of type nothing, then you cannot produce a value of ZIO of nothing. So it's going to be nothing over here, and we're also going to have fail. It's going to be over here like this. It's going to be called fail, and it's going to be like literally like mirrored, okay? So we're not going to have the a parameter, we're going to have the e parameter, okay? So the arrow is going to come in, It's going to be over here, and on the left side we're going to have the arrow, and on the right side we're not going to have anything, right? We're not going to be, we're not producing a value, we're failing instead. Okay, and so now over here we need to produce an either now. So over here we're going to produce a right, and over here we're going to produce a left, like this. Okay, so they're already finished, but as already mentioned, I'm not going to save the file because it's going to break everything. By the way, if you're coming from Tegless Final, this is where ZIO diverges a little bit from its approach. In classical functional programming sense, you kind of demonize subtype polymorphism, and so over here you wouldn't want to lose the type. If you look at something like applicative error, this would still return a ZIO of E or of A, even though A is nowhere to be seen over here, right? So ZIO tries to be very type inference friendly, okay? In fact, this is pretty much like why I'm creating this video. The majority of this video we're going to spend on making it type inference friendly and also more flexible so that more things compile, which is what variance is all about. Now, if we go and look at our flatMap and map, they're using this succeed factory, right? But now we have a way to fail, so we should probably not use them. And instead, so let me mark both of them. Instead, let's construct the ZIO manually, right? So we're just going to do this, and then we're going to have, we're constructing the thunk manually instead of going to succeed, because we might fail inside. Now let's also build the arrow channel in. In fact, if I mark all of these B's, this one, and okay, for now just this one, right? There's going to be some arrow over here and over here and over here as well. This E is always coming from here. In fact, we're going to change it by the end of this video. All right, so now when we're calling this thunk, we're not producing an A, it might be an error, right? So let's call it error or A. Okay, now over here, let me create a bit more space. Okay, so if we had an A, we would call this function, but as of right now, we actually don't have an A. So what we're going to do is we're going to do error or A, and we're going to match, and matches in Scala 3 don't require curly braces. And usually when you have this indentation-based syntax, the thing that is like coming next, it needs to be indented further, but for match, there is an exception. It can be at the same level or even further to the left so that you can write the code that we're going to write right now. Okay, so you can say case right. So as you can see, like the case is more to the left than match. Usually this would not work, but for match, there is an exception. Okay, so if we actually manage to retrieve the value A, well, then we can call this function, right? And by the way, in the end, this is going to be Z error or B, right? Okay, now if it actually failed, right? Well, then we're going to do ZIO fail, ZIO dot fail E. And there we go. In both cases, we're producing a ZIO. This guy produces a ZIO, and the ZIO fail is producing a ZIO. Okay. Now over here, this is not going to be B. This is going to be error or B, and we're simply going to return. Okay, so we simply added this pattern match on an either, and in fact, I'm going to show you a nice trick by the end of this video. I'm going to show you that there's a tiny improvement for when you're passing functions with by name parameters. We're gonna take a look at this by the end of this video. Okay, I'm still not saving the file. Okay, we need to go down and look over here. Notice that because we don't have a ZIO over here, we don't need to have an arrow channel over here. We don't need to have an either. Usually when you have map with multifunctorial types, right? So usually you would have a functor, right? It's going to be a thing with one type parameter. Over here we have a so-called bifunctor because we have two parameters. However, every time you have a multifunctors, they usually write biased. So map actually maps only the successful case, right? So if we're succeeding, right? So if we have an A, we're just going to map it to a B. Okay, like this. So same as before, this is going to be an error or A. Okay, same thing over here. Like this is going to be error or B, and we're going to do over here error or B. Okay, so we're going to simply indent this thing. We're going to take the error or A. We're going to match, and if it's a right with an A, then we're simply going to call this function. However, we need to return a ZIO, we need to return an either, so we're going to wrap this into a right. Okay, and if it's a left, well, then it's going to stay a left. Okay, in fact, we're going to recreate it. It's actually going to save us a bit of trouble later because we are recreating it. In fact, maybe I should not do this. Maybe, Yeah, let's do this for now so that I can show you this error a bit later. Let's say that this is a left at left, and we're simply going to return a left like this. Maybe it's not even going to compile right now. We'll see. Okay, so actually, I kind of believe that this is everything. No, we still have the interpreter, okay? So over here, so this is going to be some error over here, some error over here, and now when we're going to collapse it, we're going to produce either the error or the A, okay? I believe now this is everything that we need. Okay, so something that's compiled on line 27 is probably the map. Yeah, it's probably the map, right? So basically it says that, you know, that the types matched. I believe we could actually cheat a little bit because all we need to do is we need to do an as instance off, and we're going to say that this is a ZIO with error and B, right? Because there's no B over here, right? So we can select any type we want, and I believe if we do this, then it's going to shut up. Oh, yeah, we need to have an either here, right? So it's either E or B. Yeah, and now it's going to be fine, and now it actually runs fine. But this is ugly. Like, this is one of those optimizations that, you know, a real library would do. But we're simply going to recreate the left. Okay, so if it's a left of E, well, then we're just going to create another one, right? And then the type is going to match, and then it's going to be fine. Right, because over here, this was a ZIO of you know, this was an either error or A, and over here we need an either error or B. But there's no value, there is no happy path anyway, so we can do whatever we want. Now, I would like to point out two things. The first one is that we didn't touch the console, and it's because I omitted the return types. Where is it? There we go. Okay, there are no return types, right? So everything was inferred, right? So this is now a ZIO nothing unit, and this is also a ZIO nothing unit, meaning it can never fail. This one produces a unit, this one produces a string. The second thing is that since we're using an either, I hope you can develop a better intuition for why we use .exit code in the beginning of the previous video, right? So essentially ZIO inside of it. Let's actually print this out, right? So basically, whenever we're actually, you know, exploding our program, it actually in this case produces a right, and if we want it to fail, it would produce a left. Now let's actually go and try to fail. Interesting, try to fail. All right, so we're gonna go over here, and we're gonna do this, and we're gonna do ZIO.fail, boom. And it's not going to compile, and it doesn't compile because of variance. So we're going to spend the rest of the video talking about variance. And by the way, again, exceptions, they're kind of sneaky. If you try to throw something in there, right, everything is going to be fine. Well, not fine. It's broken. It's not correct. It's not caught, but it's going to compile and it's going to fail in a weird way. So be very careful whenever you call fail. Do not throw things inside, even though the parameter is by name, right? This would behave pretty much the same in the real ZIO, not only in our ZIO. And by the way, this is the print line, right? So this is the print line of this thing, okay, which is a trace failure, trace die. All right, let's switch back to ours. Let's go down and let's comment this out like this. Now, variance can be a very complicated topic, which is why I'm dedicating this entire video to it. However, if I just slap in a couple of extra characters, our code is actually going to compile. Let's actually go and do this, and we're not going to throw it, right? So we're just going to produce a value, and it doesn't compile. We go over here, and this is what I'm going to do. I'm going to fix it, and then I'm going to explain, you know, spend the rest of the video explaining the fix, okay? So we need to go over here, and we need to say that over here, this arrow channel is going to be covariant, okay? So we need to put a tiny plus over here. It is actually failing in the main. I was actually hoping that it would fail over here. Let's actually go and do this real quick. Yeah, so this is exactly what I wanted. Now it says covariant type E occurs in contravariant position, right? We're going to talk later about exactly what this means. For now, I'm simply going to hack it. I'm simply saying, okay, if we cannot use E, then we're going to use some other type, and we're going to call it E1. And this E1, it has to be at least an E, right? So this is a lower bound. I know it looks like a greater symbol, so in the past I would confuse it and I would call it the upper bound, but it's actually the lower bound. It says that the type that we're going to use here, it needs to be at least an E. So in the classical, like, you know, dog extends animal example, right? You're going to say, hey, this can be like whatever you want, but it has to be at least a dog, right? So it can be an animal, but it has to be at least a dog, okay? And now we're simply going to use this over here, E1, E1, okay? This thing compiles, main compiles, we can fail properly. Now let's explain it properly. Variance is a property of very advanced type systems that allows both the parametric polymorphism and the subtype polymorphism to coexist. Since Scala has declaration side parametric polymorphism, meaning you have control over the parameters to your functions when you declare them and not when you call them, as it is done in Java. You can add the so-called variance annotations at the declaration side and make the type system more flexible. In essence, variance allows you to have more code to compile, which is exactly what we're having over here. Before it didn't compile, we added a couple of things and then everything compiled. This is pretty much what variance is for, to make more things compile, to make the type system more flexible. We haven't changed any values, right? We just decorated the types a little bit and then everything worked out just fine. You might wonder, why do we need this? Can't it just always be more flexible? Well, in theory it could, but there are two scenarios in which the type soundness would be broken. The first scenario is mutability, and the second scenario is inheritance, not subtype polymorphism, inheritance. If you avoid these two, then you can, and let's be honest, you probably should always add variance annotations to your types, and we're going to learn exactly how to do this in just a second. A long time ago, I created a homegrown collections series which has like 40 videos or so, and one of those videos is dedicated to variance alone, even though it's 1 hour long or so. It's a very important topic, but it is a bit advanced. Now, there are three kinds of variance. You have the invariant types, it's the ones without the annotations. You have the covariant type, is the one that we just had, we added a plus, and you have the contravariant types, which are the ones that have the minus, and these are the most confusing ones. Now, Java didn't have generics for a very long time, but even Java could not resist having one of those variance types in there, namely the covariance. It is built into Java, is therefore built into Scala. It works in Scala 2, it works in Scala 3, it works in Java, and let's be honest, it probably works in almost all object-oriented languages. Let me show you this real quick. Let's actually comment out this whole thing. Okay, and we're going to do object main extends Scala app. Okay, and we're just going to do a print line hello world. I'm still used to using the curly braces, but the compiler is going to rewrite this for me. There we go, hello world. In fact, let's also have these guys, right, like this. So this is going to be a print line like this and like this. Okay, now let's say that you have the classic animal hierarchy. Now, Scala has the enum keyword, but I'm not going to use it because it's going to be confusing enough. So we're going to have abstract class animal, and we have final case class dog, and that has a name extends animal. Okay, now in order to understand variance, we actually need two hierarchies. One is going to be the one that we're going to pass around, and the other one is going to be the one that is going to get stuff passed into and produce stuff. Okay, so basically one is like the more like the data structures, and the other one is the functions or the methods. So this is going to be the second hierarchy, right? So it's going to be called abstract class animal shelter. Okay, and it's going to have a function called adopt name and string, and it's going to produce an animal. Now, covariance is we're going to talk about this in just a second. It is always the types that are getting returned, and contravariance are always the type that are being passed in. Okay, so over here we're returning an animal. Okay, so now we're going to have the implementation, right? So we're going to have a final class. It's going to be a dog shelter, extends animal shelter. This example is not going to contain generics for a while because this is going to work exactly like this in Java. And by the way, try it out in Java if you're curious. Okay, so this is going to be the implementation. Okay, well, it's just going to construct a dog like this. Okay, very, very simple. Now over here where we have the hello world, we're going to construct a shelter, and it's very important. I'm specifying the type over here on purpose. I'm going to say that this is an animal shelter, and it's going to be a new dog shelter. Classic subtype polymorphism, nothing fancy. Over here, I'm going to create an animal, and I'm not going to specify the type. I'm going to show you why in just a second. Shelter, adopt, Snoopy, like this. Okay, and now we can print line animal. Okay, nothing fancy. Now check out the type over here. All right, it is an animal. Why? Because an animal is returned. However, the dog shelter always returns a dog, right, over here. Do you think that this is going to compile if I put a dog over here, right? Is it going to compile? Because we're overriding a method. Can we just go and do this? It turns out that it does compile, and it also does compile in Java, and it also makes sense. It's totally sound. But if we go back to animal, I'm going to check out the type, and it's still animal. However, if we remove the animal shelter, then the inferred type for shelter is going to be dog shelter. and the inferred type for animal is going to be dog. It is very important to understand that whether we specify the types or not, the compiler behaves perfectly well, perfectly sound. It's all good. Nothing's going to break. Unless you do something with mutability or inheritance in a weird way. Okay, we're not doing inheritance over here. This is just subtype polymorphism, right? This is a declaration and this is a definition. There's no inheritance. So there are three types of variances. Again, the first one is invariance, and it basically means that a dog shelter can only be used when a dog shelter is required, which is not the case over here, right? So over here, we're requiring an animal shelter, but we're using a dog shelter. This is classic covariance, right? Because dog extends animal, a dog shelter also extends animal shelter. Contravariance is the most weird one, right? It's where things are flipped. Dog extends animal, but animal shelter extends dog shelter. It sounds very weird, but we're going to have an example. It's going to be, well, I'll be honest, only a little bit more intuitive. This concept is actually much more understandable if you just don't try to think about it. Instead, just concentrate on the so-called variance positions. And this is where we're going to talk about functions. Every function has two positions, the input positions and the output positions. And it turns out that always the output positions are in the covariant position, and the input positions, the parameters, are always in the contravariant position. Which is also why what I've just shown you works, because we used the types, we used the variance in the covariant position, right, which is the return types. This is also the reason why function overloading seems to ignore the return types, right? They don't participate in the so-called function signature, which is all of that stuff, the name and all the parameters, but not the return type. So if you wanted to define exactly the same function, but it would not return a dog, it would return a string or something, the compiler will say, hey, this function already exists because the return type is not part of the signature. Let's actually try this real quick, right? So if we do this, and then we're going to say string, and we're going to say hi, right? It's going to say, hey, it's a double definition, right? Because to the compiler, these two parts, right, it only looks at this. It doesn't look at the return types. However, as soon as you change one of the types, right, then the part of the signature becomes different, and now it's fine. Now, in the beginning, I said that variance is actually what brings parametric polymorphism together with subtype polymorphism, but over here, we don't even have that, right? We don't even have generics over here. Now, this actually just worked because of this hatch that just was there in Java, and it just kind of makes sense. But we're still going to bolt on parametric polymorphism just so that I can demonstrate it. Okay, so we're going to say over here that this is going to be an animal shelter of any type A. We're also going to bolt in an upper bound over here of animal. This is completely unnecessary. I'm just staying like more close to the example because it's an animal shelter. So let's constrain it so it could be anything, but like its limit is animal, right? So it can be anything underneath the animal. It can be cats and dogs, but the highest you can go is animal. So now we can produce an A over here, which again is technically unnecessary because of this escape hatch. Okay, so now over here we're going to say this is going to be an animal shelter of dog, and over here we're going to produce, still produce a dog. And now you can see why it actually worked, right? Because before it was weird, but now you see why it worked. Okay, so over here it's A maximum and animal, and over here dog remained the same. Okay, so now when we go over here, we're going to say animal over here, and we're going to see that it doesn't compile, but it does compile with a dog, right? So now if you wanted to actually make this compile, we would need to tell the compiler that, hey, we're not doing anything weird with mutable stuff. We're not doing anything weird with inheritance. So we're going to say that this A, it can be made covariant. And now more things compile, which is exactly what we needed when we had the ZIO.fail not compiling. In fact, let's actually not forget it, and let's go to our ZIO and actually add this plus over here. Now, because we're using this A only in covariant positions, the compiler doesn't bark at us. It says, okay, it's fine, okay, whatever, covariant. Let's go back to main and talk about contravariance. And for contravariance, there is no escape hatch. We will have to use generics pretty much right away. I still have a tiny hack prepared for you where you can like seemingly work around it and have it without parametric polymorphism, but there's still parametric polymorphism behind the scenes. Okay, so what we're going to have over here is we're going to have a different hierarchy, right? So we still have animal and dog, right? But now this hierarchy is covariant, and this other hierarchy is going to be contravariant, right? So we're going to have another abstract class, and we're going to call it that, a veterinarian, and a veterinarian can diagnose a dog, not animal, right? So when you're starting to become a vet, you don't know things about all kinds of animals. You're specializing on something like a dog. Okay, the dog is the only thing you need. However, a bit later, when you specialize, you become an experienced veterinarian. extends that, okay? And then you're gonna override def diagnose with animal over here, and string over here, and you're going to say animal will be fine for sure. And because there's no escape hatch, this thing doesn't compile. So over here, you see we had like animal over here and dog down there. Now it's in reverse, dog here and animal over here, but this is not going to compile. Now there's still a tiny hack that we can do, as already mentioned. So we're going to remove the def. Well, I'm actually going to do this. It's going to be faster. Okay, we can simply fall back to using functions instead of methods. Okay, so over here, we're going to say def diagnose, which is going to take a dog and produce a string. And over here, we're going to say final class experienced, no, class, not class, experience that extends that. And then we're going to do override. We can override it with a value, doesn't matter, diagnose. And now we can say animal, and we're going to say string. And we're going to say, whoa, what happened here? Equal sign, right? So we're going to say animal comes in, arrow to the right, and let me copy paste this string over here. Right, and this compiles, and it seems like it's some hack that it compiles still without parametric polymorphism. But let's not forget, like these things, they are just functions, right? So this is just function one with animal comes in and string comes out, and it turns out that if I type correctly, I'm not sure if you can actually jump in there in Scala 3, but all the functions. Yeah, we actually can. All the functions, the input parameters, which is the T1, right? It's function one. There's only one input parameter. It is contravariant, right? And all the output types, which is R, there's only one output type usually, not always, is covariant. Okay, so if you had a function 5, all the 5 parameters that would come in, that would be contravariant, and the one that goes out is always covariant, all right? But let's actually go back and not use this escape hatch. So we're going to remove this. We're going to go back over here, and we're going to use generics right away, because with generics, it's going to be fine, right? So we're going to do the same thing. We're going to say this is going to be an A. And again, we don't need to use any bounds, but I'm kind of, I kind of want to bring it back to like this whole example. We don't need this thing, right? Okay, so we have a dog over here. So we're going to use an A over here. Now it's actually not a dog anymore. It's any kind of animal, right? So it has to be at least a dog. It might actually not even be an animal, right? Because again, you kind of have like sort of like multiple inheritance in Scala. The tree might not even go to animal. Well, actually, in this case, it cannot, right? Because as of right now, the compiler sees that the dog is already an animal. Okay, so let's just call it A. Okay, some A comes in, some string comes out. Okay, and now over here, it's going to be a that of animal, right? Because it can do stuff with an animal, and yeah, over here we're just going to say animal. Okay, and now it's going to compile. I actually forgot to show you the example. I actually should have done this before. So let's go and create a that, right? And we're going to create a that of an animal. I'm going to say new experienced that like this. And we're going to print line that dot diagnose, and we need a dog. So we're going to go and we're going to create a dog, which is going to be dog. It's going to be dog Snoopy, like this. All right. So experienced that, like this. There we go. Okay. But as soon as we specialize it to dog, it's going to bark at us. Yes, pun intended. Okay, and so now we need to go there and we say, okay, well, let's make this a contravariant, and more things are going to compile. So there you have it. You have an example of covariance with a plus and an example of contravariance with a minus. And as already mentioned, you technically don't need these bounds, right? You can remove this and you can remove that. I just wanted to make this example a little bit more realistic. Okay, also print line animal over here. Now, in all of the examples that I have shown you, we actually used the covariant types in the covariant position. And we also used all the contravariant types in the contravariant position, right? So for example, over here, we said it is contravariant. Therefore, we only use it at places where it comes in as a parameter. And over here, it was covariant. So we only use it in the places where it comes out. However, what happened in ZIO was that we said that a parameter is going to be covariant, right? But we tried to use it in the contravariant position, which is exactly what the compiler tried to tell us, right? So if we revert this like this, okay, so there is no parameter called E1, right? There is only the parameter e that is marked as covariant. The compiler tells us, hey, you're using a covariant type e, and it occurs in the contravariant position. Okay, so we need to say, okay, well, let's not use it then in the contravariant position. So we need to go and we need to say, okay, well, let's use another type. And by the way, we don't need to call it E2 or something. We'll just call it E1. It's sort of like a convention. Okay, we're going to say, okay, well, it needs to be at least an E, right? So it needs to be somehow related to E. Okay, and then we're going to use that. And then the compiler says, oh, well, in this case, we're fine. By the way, either and tuples, they have all of their parameters covariant, right? So if you go into either, maybe we can even do this. No, we can't. If we go into either, as you can see, they're all covariant, right? And like usually all the ADTs, you know, lists and options and all of this stuff, all of them are covariant. Cool. Now let's also add the effect factory. Let's actually remove all of this animal and then shelter stuff. Remove all of that. There we go. Remove all of that. Like this. And these guys are going to be like this. Okay, there we go. Our fail is in there, works like a charm. Okay, we can also do just a regular string, boom. And because we're printing out the either, we see exactly our stuff. Okay, all right. So let's go to our ZIO where we have fail, right? We're going to create another one. We're going to call it effect, right? And it's going to take in an A and it's going to try to run it. Okay, so it's going to produce a ZIO of, it's going to be hard-coded to throwable and A. Okay, so what we're going to do is we're going to produce a ZIO, okay, and we're going to have an error over here, right? We're simply going to try to produce a right of an A, and if we're going to fail, then we're going to have a case over here, EX, throwable, and left, EX. First of all, when I'm going to save it, the scala FMT is going to indent this line at the same line. You can do this. It's kind of cool. You can also remove the type. You actually don't need the type over here. Also, you don't need the case. This is the only place where you can use a total function where a partial function is required. What a coincidence that we're talking about total functions again. Check this out. Okay, and now because this is a regular function, you can actually go and you can even do the underscore like this. Maybe you can even do left apply. I don't know. Left apply? Maybe just left? No. Okay, but you can do left apply. Right? How crazy is this? Okay, like this. And it is so small. And by the way, you can have them in the same line. Maybe let's actually have this in the same line. It's just that scala FMT is not going to like it. So I'm going to have them in the same line. And I'm going to do format off and format on over here. And now we can just use a regular paren over here and another irregular paren over here. How awesome this, like a super tiny try catch. Okay, so now we can go to main and we can go and do an effect over here and we can actually throw this thing and it's still going to be fine, right? So it caught the exception. It's all good. It should behave pretty much exactly like it would with the regular ZIO now, right? And there we go, right? So it interrupted over here. This is just a print line, right? This is the print line of that big thing that is coming out, which is obviously different. Now, what I want to demonstrate again is the type inference. Check it out. If we're having something like fail, right, and we do this, right, then the type of program over here is going to be ZIO of runtime exception or unit. If we don't have the fail, then it's going to be a ZIO of nothing or unit. If we have effect, right, then it's going to be throwable because we said, you know, effect, it is hard-coded to be throwable. Right, so this is what I meant. Like everything in ZIO is built for type inference. Like, look, we're still not specifying any types over here, right? Everything is done at the declaration side. Everything is done inside of ZIO for you. All right, so in the previous video, we pretty much only created the success channel, and in this video, we created the error channel. The success channel had all the fun, and it had things like flatMap and map. So let's go and create flatMap and map for the error channel as well. Now, in ZIO, it is called, the flatMap is called catchAll. So let's go and create it. So we're going to put it, let's create a little bit more space like this. Okay, it's going to look pretty much like flatMap, but I'm not going to copy paste it. I'm going to write it again. Should I write it on the flatMap? Nah, Okay, so we're going to call it catchAll, okay? And it's going to get the handler, right? So over here, we're getting the handler for the success value. Over here, the function is going to be for the error value, right? So it's going to be a function that is going to take the error, not the A, and it's going to produce a ZIO which might possibly fail with another error, right? So we're going to have E2, right? So we're going to have E2 over here, no relation to the E1, right? So there's no connection to it like over here, right? So this is a completely different type. And we're going to produce an A over here, right? And we're going to return a ZIO of E2 and A. And by the way, on purpose, I'm using A, which is a covariant type. I'm using it in the contravariant position so that the compiler barks at me again. We're going to fix that in just a second. Okay, I'm going to have the equal sign over here, and the implementation is going to be pretty much the same. All right, so we're going to have this. Okay. Like this, okay? It's just that over here, right? So if it's a right, then we're going to succeed, right? Right, so we're basically flipping them, right? So over here we had a fail, so now over here we're going to have a succeed. And now over here, you know, at the top we used to call a function, and now over here we're gonna call the handler, right? The rest is exactly the same, and now it barks at us about this contravariant type. So we need to go over here, and same as above with the E, we need to do the same thing with the A, right? Exactly the same thing. Just use the A1 over here and A1 over there. Right, there we go. It's like the inverse of flatMap. So let's go and use it. What do we have over here? So we have an effect, right? So it we actually have to throw something, right? So we're throwing the error. So we don't see this hyphen, even though like something inside of a ZIO actually caught the error, right? So it's just being like put over there. So we're gonna go over here and we're gonna say catchAll. And over here you could pattern match on your error, right? But we're going to simply ignore it, and we're simply going to succeed with nah. Just kidding. I'm actually not exploding. And there we go. It fixed it. And it works pretty much the same in the regular ZIO, as you can see. There we go. All right, so it's a success. In our ZIO, it's a right. Let's also press enter over here so that scala FMT indents them a little bit like this. Again, very important, check this out. If we don't have the catch-all, the return type of the program is throwable, right? Because it fails. As soon as we have catch-all, the return type of the program is nothing. It's not going to fail, right? We already handled all of the exceptions, right? There's still caveats, right? If you accidentally do this, it's still going to explode, right? But you're doing it wrong. Let me actually show you this this thing that I mentioned before. So this is a tiny pattern match, and every time you pattern match on an ADT, this is the catamorphism, right? So you're collapsing it, and every time you're collapsing something into a value, you can use a fold, right? So this is an either has a fold, and you pass in two parameters. It's not even curried. The first parameter is the function that is going to run when you're going to fail. The second parameter is a function that you're going to run when you're going to succeed. So this one line can actually be just written as error a dot fold. The left parameter is what are we going to do when we're going to fail? Well, E is going to come in and we're going to fail, right? Was an E. And on the right, we're going to say, well, the A is going to come in and we're going to call AZB with an A, okay? Like this. Everything should behave exactly the same way. Now, over here, like AZB is a regular function, right? A comes in, ZIO comes out, which is exactly what we needed over here. So then we can write AZB, right? Like this, shorter. Over here, we need a function. If we go to fold, right, it's gonna need a function that is gonna take the A, which is the error channel, and produce a C, which is ZIO in our case, right? However, ZIO.fail actually has a by name parameter. Remember? So in Scala 2, you would not be able to use the same add expansion. In Scala 3, you can. You can just go and say ZIO fail, right? ZIO fail, like this. Right, this is just one line, and now you see if we go down, to here, to flatMap, over here, right, like this, and like that. Then we're going to fold, okay, and then on the left, we're just calling the H, and on the right, we're just succeeding, right? Again, like succeed has a by name parameter. In Scala 2, this would not have worked. Look at this tiny code. But actually, we're going to revert it for now, for clarity, and also we're not done building our ZIO, so I believe this is going to be simpler to extend, at least for now. But it's actually kind of cool. We're already reaping a lot of benefits from Scala 3. Let's not forget that we also wanted to have a map for the error channel. Let's go and edit. So we have flatMap map. Now we have catchAll, and this is going to be the regular map. Let's actually copy the whole map. we'll be fine. Like usually when I copy stuff during videos or in general, then I'm making errors, but hey. Okay, so we're gonna have a map error, okay? So over here, like the A is going to stay the same, right? So the A is going to be returned, which is why we don't need the B parameter, okay? But we're going to produce another error, right? We're mapping the error, okay? So over here, we're gonna take the error and we're gonna call it handler again, right? We're gonna take the error and gonna map it to E2, right? So it's very similar to the regular map, but the map maps the right side, the map error maps the left side. The implementation is the same over here. When we're producing a left, we're still going to produce a left, but we're simply going to call the function over here instead of over here, right? And over here, we're just going to return the value. And this is it. What do you want? Like I love this plugin. Like I used to love it in Scala 2 because it would show me the first line of the error message. However, Scala 3 started displaying messages like this, so that the first line is kind of useless. So I always have to do like this and see, oh, okay, so I found either E2 of A, but it required either of E or A. Why did you require that? You actually needed to require, yeah, I forgot the E2. Okay, like this. And this is actually error or, well, hold on. This is actually error or A1 technically. Well, actually, it's not A1. It's still error or A. How am I going to call it? Well, it's different error or A, right? So we're going to call it E2 or A, right? So this one is going to be error 2 or A. This kind of makes more sense, right? Did it make sense over here? No, over here, it's actually kind of like this, A1, 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 A1. This makes sense, right? So this is a, yeah, E2 or A1. Okay, so this is 0, error 2 or A1, right? So 0, error 2 or A1. Error 2 or A1. It doesn't really matter. Like in the real library, this whole line would be just like collapsed into just one tiny line. Now let's actually not forget to go and use the map error. Let's go over here, and over here we're going to, so we're not going to catch it, right? So we're going to do map error, and the classic example is to do, get message. Okay, so now we're going to boom. So before we were doing this, and now we're doing, and also the types again, right? So over here, let's see, what do we have? ZIO throwable. Let's see if this is going to change. Let's see. It's a ZIO string. How awesome is that? All right, now let's actually revert the failure. I don't like the failure. Nobody likes failure. And yeah, this is pretty much all I have for you today. And in the next video, we're going to introduce our third and final parameter. By the way, a lot of signatures inside of ZIO, they might end up having I've seen signatures with up to 5 type parameters. And I don't think it's going to stop there. We might actually see septifunctors or something like this. In any case, that's all I have for you today. In the next video, we're going to have the reader introduce the third parameter and the last parameter. And for now, as always, it's been Vlad, devinside.com. Don't forget to like this video if you did, subscribe if you want to improve the developer inside you. And if you learned something today, please consider supporting me on GitHub sponsors or Patreon, whatever you prefer. And that's watch my videos weeks and sometimes even months before everyone else. And then maybe one day I'll be able to do this whole content creation thing full time. In any case, take care.